This is Further Pure 1 Reducible Differential Equations. Reducible differential equations is the last chapter in your Further Pure 1 book, and it covers what we do with certain types of differential equation that on the surface don't look like we can deal with them. It's a lot like integration by substitution. There are numerical methods, and just like with tricky integrals, we could resort to the trapezium rule, mid-ordinate rule, Simpson's rule. If we were trying to solve a differential equation, we could find the Taylor series expansion at a particular point, or we could use Euler's formula or the midpoint method. But if we're looking for an exact solution, an analytical solution, to get the precise function that represents y for the differential equation, it's not always that straightforward. Here's a couple of equations that we can't solve. I'd encourage you to pause and have a think about why we can't solve these directly. What is it about them that makes them difficult? All right, here's a couple of things. Nonlinear and non-separable. The equation on the left cannot be written in a form that would allow us to use the integrating factor, and it can't be written as a function of y on the left with dy and a function of x on the right with the dx. So we can't solve it in the ordinary methods that we've learned. The equation on the right doesn't have constant coefficients. It's got an x squared in front of the second derivative of y. It's got an x in front of the first derivative. So it doesn't fit the standard format that we're used to dealing with when it comes to second order differential equations. But it turns out the right substitution will let us crack open these equations and turn them into a form that we can deal with. Remember, these are the key methods that we might have come across for first order differential equations. You can either integrate directly because everything on the right hand side is a function of x, or you can separate the variables because it's possible to rewrite them as a product of two distinct functions, one of x and one of y. In the case where you've got a function of x multiplied by y, and then some other function of x added on, we can use the integrating factor. But if we've got something else, then we can't necessarily solve the equation. For second order differential equations, arguably the simplest sort would be the kind of thing you might have done at the end of A-level maths when you were looking at kinematics with acceleration, velocity, displacement. If you know the acceleration in terms of time, you can integrate twice to find the displacement in terms of time. You just need a few extra initial conditions to substitute in. The standard sort that you've come across this year will be homogeneous second order differential equations, which basically means there's a zero on the right, but we've got constant coefficients in front of the derivatives on the left. And we would just use the auxiliary equation. We'd find the roots of those, and depending on their nature, whether they're complex, real, repeated, we would identify the appropriate general solution to construct. And then in the third case, where we have some other function of x on the right-hand side, we could still use the solution from the homogeneous case, but we would have to add on a particular integral. Anything else other than those two forms, we can't directly deal with yet. Let's have a look at how this substitution allows us to break apart that first equation. Z equals y over x. The reason this seems like a sensible substitution is that y over x appears on the right-hand side, and x over y is also there. So in a sense, all the different terms are already in terms of z. But the thing we've got to be careful of, and it's the same with integration by substitution, is that the derivative terms also need to be changed. If you've got an integral with a dx, the first thing you do with substitution is find the link between dx and du if you're making a u substitution. And it's the same thing here. Here's how you might go about this initially. You might decide that you need a link between the derivative of z and the derivative of y. So we differentiate z with respect to x. Now z is already y over x, and you've got to be really careful with your implicit differentiation here. We're differentiating with respect to x, which means anytime you differentiate a function which is not a function of x, you need to remember to use d something by dx. For instance, y over x, using quotient rule, we have the bottom x multiplied by the derivative of the top, dy by dx, minus the top y multiplied by the derivative of the bottom, which is 1, all divided by the bottom squared. So this is quotient rule applied using implicit differentiation. Once we've got that, we could rearrange, simplify a little bit, so we can turn that into 1 over x dy by dx minus y over x squared. And then with a bit more messing around, we can perhaps rewrite it in a form that's a bit easier to work with. In particular, what I've done here is found dy by dx in terms of other things. My focus here is on getting rid of the dy by dx term in the original equation, because I can already see how I'm going to deal with y over x and x over y. Those are going to fall apart very easily and turn into z's. So at the end, we could eliminate y by replacing dy by dx with x dz by dx plus z, because y over x, remember, is the same as z. However, this process we've just gone through here, although it seems logical and it will work, it's a little clunky and long-winded compared to this alternative. If you rearrange first and then differentiate y with respect to x, this is slightly more efficient because it immediately gives you dy by dx. So what I'm doing here is writing y as xz, and then I'm going to differentiate using the product rule this time. X times the derivative of z with respect to x plus z times the derivative of x with respect to x. You'll notice that this gives us straight away exactly the same thing that we had down there, but it gives us it in 2 lines instead of 5. Once we've got that, whichever direction we came from, we can go back to the equation, replace dy by dx with this thing, replace y over x with z, replace x over y with 1 over z, and now, if you look carefully, you'll notice we've got some things that cancel out. We'll be able to eliminate the plus z from both sides for a start, and then this equation actually becomes a variable separable differential equation. We can multiply both sides by z, divide both sides by x, multiply by dx, or more formally integrate both sides with respect to x, and we end up with this thing. So z squared over 2 is minus ln x plus c. Of course, at the end, just like with substitution when you're doing integration, you need everything back in terms of y and x. So we're going to take our z and replace it with y over x, and then ideally do a little bit of rearranging, simplifying. And if you can, or if it's not too horrible to do so, it's usually nice to write in terms of y. So in this case, we're able to get an explicit form for the function, y equals some function of x. Not a particularly pleasant one, and perhaps it would be nicer to write 2 ln x rather than ln of x squared, but I'll leave it like that. Here's a similar one. You're going to use the same substitution, but we have dy by dx equals x over y minus y over x. What often surprises me about these questions is how different the process can feel if you make just one small change. Tweak one thing, try putting a 2 in front of one of these, and often the entire process can change because the integral will be modified just slightly. Give it a try, and when you're ready, unpause the video and we'll work through and you can compare line by line to what I get. Okay, the first thing I'm going to do is rearrange, just like with the last one. Y equals xz will give me the same thing we got last time, a direct link between dy by dx and the rest. I can get rid of dy by dx, replace it with things that only involve x, z, and dz by dx. When I substitute that in, and also get rid of the x over y and the y over x, I'm left with this. Now last time, the z's on each side cancelled out. This time they don't, but they do combine a little bit. When we put everything together in this form, we can see that it's still a variable separable differential equation. Everything on the right involves z, and everything on the left involves x at the moment, other than the derivative term dz by dx. So I can divide both sides by the function of z and the function of x, multiply both sides by dx, and integrate. We get something like this. So simply because the z's didn't cancel out, we've got a more complicated looking integral on the left-hand side, but it's still something that we can work with. In this case, hopefully you noticed before going through the rigmarole of partial fractions that this particular case is an example of the top being related to the derivative of the bottom. Whenever you see a fraction that you're trying to integrate, the first thing you look for, the triage process that you go through at the very beginning, is to see if there is a quick and easy inspection result. And the most common one that I look for, particularly with fractions, is can I make the numerator the same as the derivative of the denominator? Can I get the top to be the derivative of the bottom? And the bottom of this fraction differentiates to minus 4z. So as long as I can get a minus 4 on the top, which I can do by putting a minus a quarter outside, and then it doesn't change the value of the integral, now I'm looking at an integral which is exactly the form that I need. So I can integrate it to get ln of the denominator. If you've forgotten this trick or you're a bit rusty on it, then the way to remember is that if you were to differentiate ln of something, you would end up with 1 over the something multiplied by the derivative of the something. That's how chain rule works. So we're essentially reversing chain rule in the specific case of ln. Now we have this, the next thing to do will be to try to rewrite in terms of z a little bit so that we've got something a bit nicer. And once I've done that, rearranged, reversed the logs with a bit of exponentiation, then it's going to be time to simplify things further. You'll notice that instead of writing e to the ln of something minus something else, I've simplified both of those sections. E to the ln of x to the minus 4 is just x to the minus 4, and e to the minus 4c can be written as a whole different constant, a. And then I'm going to resubstitute at this point, so I can replace z with y over x. And then I've got a bit more work to do to get y squared in terms of x. And this, incidentally, is the curve that we end up with. Very pretty. This particular one you might remember because it appeared in a previous video when we were looking at Euler's method. We actually solved numerically this same differential equation. Now we're seeing how we can construct the actual function that represents this one. Now you can have a go at a few questions from your book, exercise 9a, questions 1, 5 and 6. When you're ready, come back to the video and we will continue. Now we're going to barrel ahead and look at how we can reduce second order differential equations. We're going to use a very similar technique. We're still going to be provided with the substitution to use. And in this particular question, they've given us the big nasty looking equation that we start with, and they've also provided us with the equation we're supposed to demonstrate we can reduce that to. There are a few clues you can pick up straight away by looking at that. For instance, there's a 1 minus z squared in the equation we're working towards. And if z is equal to sine x, then 1 minus z squared will be 1 minus sine squared x. In other words, cos squared x. So it's quite likely that there will be a cos squared x term towards the end that I can reduce and turn into 1 minus z squared. The other thing to notice is the derivatives that you have in the original equation, in this case, the derivative of y with respect to x and the second derivative of y with respect to x, and contrast those with the derivatives you're going to need at the end. In this case, still a derivative of y, but with respect to z. Now, the first derivative of y with respect to z doesn't appear in this equation, so presumably those terms, if they appear at all, will cancel out. But there should end up being a second derivative. Now, the first thing we do is pretty much the same every time. We're going to use the substitution we're given to form a link between derivatives. So I'm just going to differentiate z equals sine x with respect to x. That gives me dz by dx. And on its own, dz by dx doesn't look particularly useful. We have already an equation with derivatives linking y and x. What we want is a derivative linking y and z. And what we've got is a derivative linking z and x. But in fact, that triplet of derivatives, they're all connected to each other. dz by dx can be our middleman between dy by dx and dy by dz. So if we put it together carefully with chain rule, we can see that in action. We're looking for a way of eliminating dy by dx and ultimately also the second derivative. But for now, dy by dx can be turned into something involving dy by dz and dz by dx. And of course, remember, dz by dx, we already know, is cos x. So we can swap that out straight away, and we've got a way of writing dy by dx in terms of cos x still, but dy by dz as well. The next thing we're going to do It's probably fairly logical as well. We're dealing with a second order differential equation. It's not enough just to be able to eliminate dy by dx. We also need to be able to eliminate the second derivative, d2y by dx squared. So we're going to take this expression we found for dy by dx and we'll differentiate it one more time, also with respect to x. Now take care with this, because when you're differentiating with respect to x, any functions of x will differentiate ordinarily, and that should be fine. But if it's a function of something else, or if it's a derivative with respect to something else, then we need to remember how implicit differentiation works. We need to take into account chain rule. Now, this particular one is also a product rule situation, so we'll need to write down cos x and multiply by the derivative of dy by dz, then write down dy by dz and multiply by the derivative of cos x. But each time we write down a derivative, it's the derivative with respect to x. So we should get something like this. If we want to differentiate dy by dz, we end up with the second derivative of y with respect to z multiplied by dz by dx. dz by dx is the adjustment factor. It's the thing you multiply by if you've differentiated with respect to z, but you were actually supposed to differentiate with respect to x. Just like if you've calculated the weight of something in pounds instead of kilos, you multiply by your adjustment factor of 1 over 2.2, and that will do the conversion for you. So this is the adjustment factor that allows us to change something that we've differentiated with respect to z into something which has now been differentiated with respect to x. Next, I am going to multiply by cos x. Now, there's a very good reason for this. I am attempting now to substitute into the original equation, and I've noticed that we have cos x times the second derivative. And so if I do that now, before I start substituting in, hopefully my working will not look quite so complicated and confusing. Feel free to do this next couple of steps all in one go if it's easier for you. But I'm going to multiply everything on that line above by cos x, and then I'm going to substitute it into the original differential equation, and I should get this. So this stuff here is the very first term. This is cos x d2y by dx squared. We also have sin x times dy by dx. And remember that dy by dx is cos x dy by dz. The rest is written as is. Now straight away, if you're paying attention, you'll see a couple of things cancel out. We've got a sin x cos x dy by dz and a minus sin x cos x dy by dz. So those two disappear, and that's why the first derivative doesn't appear in the final iteration of the differential equation, the one that we're working towards. We still have cos cubed in front of the second derivative of y with respect to z, but I'm not too worried about that because cos also appears in relatively high powers in the other sections of the equation. Maybe you can start to see where this is heading now, particularly if you compare it with the version we're trying to get to. So once I've written that out without those cancelled terms, I can see straight away that I could divide through by cos cubed x. Once I've done that, it looks very similar to where we're trying to get to. The only difference is the thing we mentioned at the beginning. We have cos squared x. We can replace that with 1 minus sin squared x, which in turn is 1 minus z squared. You could, at this point, if you wanted to, go on to solve this equation. It is now a non-homogeneous second order differential equation, but I'll leave that up to you if you want to refresh your memory and give that one a try. The trick is, once you've found a solution in terms of y and z, going back and replacing z with sin x will give you a solution in terms of y and x. You should now be able to have a go at another question. The question we've just done is question 4 from exercise 9b. You can try question 5. When you're ready, we're going to do a couple more examples. So this question is a good example of a modeling situation. This is from the mock paper for Further Pure 1, and they're describing an antibiotic which is given to a patient. We're monitoring the concentration of the antibiotic in the bloodstream. The concentration is given by x, and the time that goes by in hours is given by t. And the first thing to notice is that this differential equation is not one that you can solve directly. We've got 2x multiplied by the second derivative of x, and also we've got dx by dt squared, so it's not even a linear differential equation because we've got terms involving x multiplied by one another. X or its derivatives don't just appear singly on their own with constants or with functions of something else in front of them. Be careful here because the situation is x in terms of t rather than y in terms of x or something else. So keep an eye on which variables you're interested in and which ones you want to try to remove or change. So we have x and dx by dt and d2x by dt squared, and we want something involving d2y by dt squared. Here's the steps that I would recommend you follow. I would start by using the substitution given, y equals 1 over x squared, to find a link between dy by dt and dx by dt. You can do that by differentiating with respect to x. Then, once you've got an expression for dy by dt, you can differentiate one more time and you can get a link between the second derivative of y with respect to t and the second derivative of x with respect to t. Once you've done that, you should be able to substitute back into the original differential equation, simplify things. Remember, when you're dealing with functions of a variable other than the one you're differentiating with respect to, you need to remember chain rule. And if you've got the product of two functions, you'll have to make sure you use product rule carefully as well. The next thing to do for the next part of the question is to solve the differential equation. To find y in terms of t, that should be relatively easy. Once you've performed the substitution, it's a fairly nice differential equation to solve, as non-homogeneous second order differential equations go. And then you need to identify the variables for the initial conditions. Be careful with this, but you can do this in terms of y and t. It doesn't have to be in terms of x and t. You can sort out your initial conditions and therefore find the constants all originally before you change everything back. So your initial conditions will be in terms of the new variables. You can find any constants from those. And finally, substitute back the given information, solve the resulting equation to find t, and then interpret your results. That means you go back, you double check the units so that you know exactly what it is you're calculating and what it represents, and then find the time it takes for the concentration to halve. Think about which measurement is going to change and how it's going to change. Pause, have a go at this fairly meaty exam question. It's 16 marks worth, so give yourself a good 20 minutes, I would recommend. And when you've had a go at it and you're ready to see my solution, then continue the video. All right, we're going to start with the first part. So let's focus on how we can use the substitution to transform the differential equation. Start by writing this as y equals x to the minus 2. Then I'm going to differentiate with respect to t. Now, this is not the only way to do it. You can differentiate with respect to x and use chain rule directly. But it's also possible to say, well, actually what I want is dy by dt. So I'm going to differentiate with respect to t. And on the right-hand side, that means differentiating implicitly, which means I've differentiated with respect to x and then multiplied straight away by dx by dt. Then I can differentiate a second time, also with respect to t. And when it comes to the minus 2x to the minus 3 term, that differentiates to give 6x to the minus 4 dx by dt, because remember we're differentiating with respect to t, so differentiate it with respect to x, but then multiply by dx by dt. And then we still have a dx by dt term there. Using product rule, we're then going to leave minus 2x to the minus 3 unchanged and differentiate the dx by dt with respect to t. And that will give us just the second derivative, d2x by dt squared. Once you've got both of those, probably the simplest way is to look at your dx by dt in terms of dy by dt. So over here on the left, we've got dy by dt equals minus 2x to the minus 3 dx by dt. Therefore, dx by dt can be replaced with minus x cubed over 2 dy by dt. Similarly, the second derivative can be rearranged so that we've got a way of replacing the second derivative of y with respect to t with something involving the derivatives of x with respect to t. Now this looks a little strange, But you'll notice with a bit of mucking about, you can get it in the form where the substitution becomes quite natural. You may well have had a different route through, so it's worth trying this a few ways, and you will not necessarily find the most efficient route the first time through. Some of these can be quite messy algebraically, and although the theory behind it is not too crazy, in practice they can often be a little confusing to work your way through successfully all the way from the beginning to the end. What I've done here essentially is multiplied through by x to the 4, partly because the two terms I had there both involved negative powers of x, but also because I had one eye on the differential equation that I'm trying to work with, and I can see that it's got 6 lots of dx by dt squared, whereas I had 6 lots of dx by dt squared multiplied by 1 over x to the 4. And a similar thing was happening with the second derivative here, comparing to that. Once I've got that, I can take 2x d2x by dt squared minus 6 lots of dx by dt squared. Notice that that is actually perfectly the two terms at the beginning of my differential equation, and that can be replaced all in one go by minus x to the 4 d2y by dt squared. That allows me to swap those out directly. So here's the original differential equation, and then we make the substitution. So this piece here disappears and gets replaced by this piece here, because this. Once you've got that, it's just a case of rearranging a little bit and seeing what cancels. So in this case, I've divided by x to the 4 so that I can get d2y by dt squared on its own, just like in the equation I'm trying to get to. And then I notice that I'm very nearly there. Y is equal to 1 over x squared, so I replace that with y and I add 3, and we've got the differential equation we needed. Remember, this is not the only way to do this, but I think it's useful to show the implicit differentiation right from the start approach, because sometimes it can be a little more efficient. And if you already know the format you're looking for, and if you keep an eye on both equations, the one you start with and the one you're working towards, you can often find that there are more efficient routes through with these questions. This next part of the question is where most of the marks are going to be found. So we'll get these marks by solving the differential equation that we've just managed to construct, and then also for using our mathematical modeling skills to interpret the information given, to make sense of that in terms of these new variables, and then to convert back at the end so that we can give an answer in terms of the original variables. We're interested in when the concentration will be halved. In other words, when x will go down to half of its original value. The first thing we can do though is solve this differential equation. It's a second order non-homogeneous differential equation. So we can find the complementary function by using the auxiliary equation. We get m squared minus 1 equals 0. So we have two distinct real roots, and that gives us a clue as to the format for our general solution. However, so far we just have a complementary function. We've got the right format for this bit, but we also need the particular integral to make a complete general solution, because this one is not a homogeneous second order differential equation. This one's got a constant on the right hand side. So we're going to need to make a trial function like y equals lambda. And because the derivative of a constant is 0, and therefore the second derivative is also 0, this makes for quite a simple equation. If we try substituting this in, we'll find that the only value of lambda that works is negative 3. So we're going to add the complementary function and the particular integral together, and this will give us our general solution. Now the next thing we need is to take into account the initial conditions that have been described in the question. When the dose of the antibiotics was given to the patient, that's another way of saying t equals 0, because t is measuring how long it has been since the dose was administered. The concentration was 2 milligrams per liter. Well, x is measuring concentration, so this is a way of saying that when t is 0, x is 2. The next one, a little more complicated. This is the rate of change of the concentration. That's dx by dt. It's the rate at which x changes as time goes by. And if you're unsure of the units, you can double check over here. 1 milligram per liter is how we're measuring concentration, just like this one is 2 milligrams per liter. But 1 milligram per liter per hour means we're measuring concentration per unit time, so dx by dt. So without further ado, let's see if we can make use of those. Unfortunately, our equation involves y and t, not x and not dx by dt. However, we do have this equation that we can make use of here. Y is equal to 1 over x squared. We know that was the original substitution provided for us. So if we know what x is at the beginning, then we know what y is. It's 1 over x squared, or 1 over 2 squared in this case, and therefore a quarter. Not only that, but we've got an expression from our previous working out for dy by dt. We worked that out by differentiating the above substitution y equals 1 over x squared with respect to t, or you can differentiate with respect to x and then use chain rule. Either way, you'll end up with this. Direct connection, meaning that if you know x, which is 2 at the beginning, and you know dx by dt, which is 1 at the beginning, you can work out dy by dt at the beginning. We substitute those numbers in, we get minus a quarter. Then we can return to our general solution, and we'll start by putting in the first set of conditions. We know that y is a quarter when t is 0. So we sub in t as 0, we sub in y as a quarter, and we've got an equation linking a and b. The next thing we look at is the derivative. So if we differentiate y with respect to t directly from our general solution, it's relatively quick to do because exponentials are nice and easy to differentiate, and we get this. We can then substitute the value we know for dy by dt, because when t is 0, dy by dt is minus a quarter. So we get this. Now these two simultaneous equations can be solved very easily. You could add them together, for instance, or you could rearrange a little bit and substitute in the calculator if you wanted to, but you should find that a is equal to 1.5 and b is 1.75. Once you've got those values, you have the general solution. Remember that when x is 1, y is 1, and x is 1 is relevant because the question was asking, find the time taken for the concentration to be halved. In other words, how long will it take for the concentration to go down to half of its initial value? And remember, initially it was 2 milligrams per litre. So we want to know how long it will take for x to drop from 2 to 1. And the simplest way to do that is to double down on our equation linking y and t. Let's keep everything in terms of y and t, and any information the question gives me in terms of x or its derivatives, I'm going to convert to my new currency. So x equals 1 gives us y equals 1 over 1 squared, or also 1. Then we can substitute into our newfound particular solution, which is y equals 3 over 2 e to the 2 plus 7 over 4 e to the minus t minus 3. And we can rearrange and solve. To solve equations like this, remember, you're going to want to multiply both sides by e to the t, and then you can hopefully see it as a disguised quadratic. We've got 6 lots of e to the t squared minus 16 e to the t plus 7. So treat it as a quadratic in e to the t. You can even use the calculator to solve the quadratic layer, or the quadratic formula, or completing the square. And once you've got the values for e to the t, you can find the relevant values for t. In this case, we've got t equals 0.749, and therefore we have 45 minutes to wait for the antibiotic to go down to half of its value.